So welcome everyone to this new session of our category seminar. It's my pleasure to introduce today's speaker, Ross Street from MacQuarie University, who will be speaking to us about centers of monoidal categories. The title of his talk is Views of Centers. If at any point anyone wishes to ask a question, please unmute yourself and ask the question at any time during the talk, or write the question in the chat and then we can read it back to Ross. Well, thank you very much, Ross. Take it away.
Oh, thank you very much, and thank you very much for the invitation, Juan. I've been looking forward to the talk. I hope it works out. I've chosen this topic about centers. It might be a bit of a long talk. I hope I can get through it all in the time. I don't want to go too fast. So the plan of the talk is, first of all, to give an eccentric look at the structures of interest, like monoidal categories and braided monoidal categories and so on, just the way you might discover the axioms and so on, just by thinking of them as, thinking the morphisms first. That's the idea. It's not that important for the rest of the talk, but I thought I wanted to do something a little bit different than just define the center. Doesn't seem to be moving on too easily. Yes, okay, has that moved on? So the second topic will be to give all the different types of centers. There's a center of a category, the center of a bicategory, center of a monoidal category, the center of what I'm calling monoidals, which are pseudo-monoids. It's just like locale, I thought monoidal. I don't like saying monoid object in the bicategory or monoidal object in the bicategory. So that's a pseudo-monoid anyway, in a braided closed monoidal category. So then I want to go through our original reason for actually putting the concept of center in a paper. And that's a joint paper with Andre Joao on Yang-Baxter operators and tortile Yang-Baxter operators. I want to just give the heart of that, how you use the center to do something there. Then I want to discuss Davidoff's full center, which is another idea on the center when you don't have a braiding, and I want to show that that is actually a center of a monoidal. Then I want to sort of head towards some work by Tureev and Virolesier on G categories, where G is a group. And the main point there is to get in, so show how you can get a higher version. So I guess my main theme is all the different levels at which the at least 1, 2, and 3 dimensions you can get the notion of center, and so a higher full center in the Davidoff sense, but now instead of for monoidal categories, for the monoidal bicategories. And the reason that Tureev and Virolesier were interested in this was they were trying to prove Muger's theorem, which is about how much better the center is than the original category, more or less, not necessarily just having a braiding in the context of fusion categories and things. Okay, so let's get on with this eccentric business. I'm going to call a magma is just a set with a binary operation. So a right unital magma, which I'm calling a rumor, is a set just equipped with a binary operation and a particular element that acts as a right unit, as you'd expect. And you just call it a unital magma when it's also the left unit. And just call it I'll call that a UMA. So any monoid, of course, is a UMA, in particular the endo functions of a set, just using composition and taking the identity. And if you can define morphisms without any more structure. The rumor morphism is just the usual definition in a variety, preserving the operations. And I also want to have this concept of a comorphism or commorphism that's more for commutativity than for dual. And that comes from any set into a rumor. You call it a commorphism when the images commute. So f of A times f of B is f of B times f of A. And I just remind you of the usual Ekman-Hilton argument. And that is that if you have two magma structures on the same set and they have the same unit, then the two things agree, and the structure is not only commutative, but you also get the associativity out of all that as well, out of just the fact that one's a morphism for the other. So when you have a binary operation, you can look at left multiplication by that as a function from the object, from the magma into the endomorphism monoid. And if you look at what it is for that to be a rumomorphism, then that's exactly saying that A is a monoid. And to say it's a commorphism turns out to be saying that it's a commutative monoid. You again get the commutativity and associativity out of it. So that's a good little exercise just to see that the commuting of the in the codomain there gives you associativity and commutativity. You get the commutativity first, and then you use that to get associativity. So as I'm saying, it's the associativity comes out in that second case too. So I want to go up to categories now and do a similar thing, and you have to take more steps as usual because you have another dimension. So a right unital magmal or a rumal is a category equipped with a tensor functor and an object and the natural family of left unit constraints, you might call them. Oh, I've got it on the wrong side, have I? Oh dear. Why have I called that? I've got that the wrong way around. Right unital. That's actually left unital, isn't it? Yeah, okay, that's just a typo. So any monoidal category gives an example as before, and I'm writing big L for the tensor, left tensor product, tensoring on the left. Now this is the main point I'm trying to make, that you can talk about it even at this level, just having the tensor product without any associativity constraints. You can talk about a morphism of Rumal things, which is just a functor which has constraints which that it preserves the tensor product up to isomorphism and preserves the unit. And then you have an axiom which connects the two things a little bit. I've got it on the right side this time. But the arrow's going the wrong way. Is it? No, I think the row A should go from A tensor I to A. That's what I should have had in the previous screen. So it turns out that a Rumal morphism structure on the functor, if you look at what it is, remember that the structure on that endo functor category is a strict monoidal category. It turns out to give you associativity constraints and the left unit constraint. And you get this axiom connecting the left unit constraint and the right unit constraint and the associativity, which is a familiar axiom for monoidal categories, but we don't get the associativity yet. I'm calling that a premonoidal category when you get this extra relationship between the unit, left unit and right unit constraints, that they agree on the unit. Anyway, I just think it's interesting that when you write down the axiom for that to be a strong monoidal morphism, then well, this is the definition of the strong monoidal functors. You can call them strong monoidal functors between premonoidal categories when they satisfy these two axioms, which are together with the previous axiom for the right unit constraint. This is somehow looking as though if you didn't have invertibility of the F2, this it's a bit like saying if F itself is a monoid, right? This is like the first diagram is a associativity, and then the other two unit things are like unit conditions for a monoid. So if you ask for a strong monoidal structure on this left multiplication functor, it turns out to be a monoidal structure. So you get the MacLean pentagon because that hexagon that was on the page before, because you've got associativity constraint in the endo category being the identity, you only get a pentagon. So anyway, that's how it all pops out. And then you get a kind of, well, you can do a bit more with the Ekman-Hilton argument than what I've got here, but let's just say it this way, that if you ask that your tensor product is actually a morphism for itself, strong monoidal for itself, then you get this middle of four, I like to call it, rule, which gives you a braiding. And that was one of the ways of coming at the braiding, for me anyway. And it was actually inspired by Bob Walters. Bob Walters and Levere were talking, and they sort of assumed that if you had this property, then you'd get a symmetry. And it turns out it isn't quite a symmetry, and that has big repercussions. So I do want to talk about Yang-Baxter operators later. Later, I'll just be talking about Yang-Baxter operators on an object of a monoidal category, but you can do it for a functor from any category into a monoidal category. And just so I can draw the diagram, I'm assuming the monoidal category A is strict at the moment. So Yang-Baxter operator is a bit like that thing. It's a higher version of the commorphism. It's a functor from just a category into well, in this case, strict monoidal category, giving the commutativity of the images. And then you've got an axiom on the Yang-Baxter operator, which is a hexagon. And yeah, if it's just a monoidal category, then and not strict, then you've got to put some associativity constraints in there, of course. So I think it's an interesting different point of view on. I noticed that Runkel is speaking next week or next talk anyway in your seminar. Anyway, Davidoff and Runkel defined a B category to be, well, they didn't say it this way, but it turns out it's the same as saying that this left multiplication thing from A, where you're not using the structure on the domain A, but well, let me say it this way. You can think of a B category as just being a functor from A into the strict monoidal endo category AA, bearing a Yang-Baxter operator. And so that functor L gives you a tensor product because it's the same as something from A cross A into A. And yes, as I say there, and we get the magmal structure on A with that, and the natural family of isomorphisms beta, which have the bracketing in, and it's kind of, you see that each braided monoidal category gives you such a thing by taking the beta to be sort of conjugating by the associativity constraint, this gamma tensor 1. So you can do a bit just with that structure. And the axioms for a unital B category, there are 2 extra axioms on the unit constraint, which I won't write down, but you can see this is how, once you've got the right unit constraint with 2 axioms on it, you can get a braiding out of it, and then you get the associativity, just as in the simpler case, you could get the commutativity of that, whatever I was calling it. Yeah, from the Yang-Baxter, or from the Commorphism, we got it before. So anyway, they have this theorem that you can go, it's not completely trivial, it's quite a kind of interesting proof, even though I think the 2 axioms on the right unit constraint are quite complicated. But you do get the same thing as the braided monoidal category. And then they use that and go on to do cohomological things. Okay, so now to do some centers. So if you take any monoidal category and the tensor unit, then the endomorphism monoid of that unit is commutative. And that's basically because you've got the 2 operations, the 2 monoidal operations on there. You've got composition and this kind of, well, it's really basically tensor. If it was a strict monoidal category, it'd just be tensoring, but it's kind of a convolution with the unit constraints, and yeah, on either side. So that gives you a commutative monoid always, and that's probably the basic idea of center. But in particular, if you just take any category, then you get a strict monoidal category by taking the endofunctor category. And the unit is the identity functor. And the monoid as above, when V is this endo category, is just the natural transformations from, I'm using square brackets for the functor category. I guess I should have said that earlier. So this is just the natural transformations from the identity to the identity. And that becomes, let's call the center of the category, A. In particular, if the category is just a 1 object category, which is a monoid. So if you take a monoid, the center of a monoid is really the center of the category, where you regard the monoid as a category, as I will from now on. A monoid will always be a category with 1 object, and the object I'll either call 0 or 0 sub m. I think maybe later on I call it O sub m, little o sub m. And you note that this really can be put as a limit construction. It's just the equalizer of a reflexive pair of 2 maps. One is left multiplication, one's right multiplication. And then you can define the center of a monoid in any braided closed monoidal category just as an equalizer with the same notation as above. You can define those maps D0 and D1 using the braiding, and you've got obviously need the closed structure too for the to get that home. And now just pushing it all up 1 level, the center of a bicategory. If you take a monoidal bicategory, again, the unit now becomes a braided monoidal category by the kinds of arguments we've talked about. So we've got, again, you've got 2 operations on or you can just say that you can prove directly that the composition operation is actually a morphism for itself, and you get a braiding. And so in particular, you can take a bicategory and look at the pseudo-endofunctors of that bicategory. So a pseudo-functor is from a bicategory to another bicategory is like a functor, except that it only preserves the composition and the unit up to isomorphisms, which have coherence condition. And so you get a braided monoidal category by the process in the dot point above, by just taking the pseudo-natural transformations from the identity pseudo-functor of K to itself. That's called the center of the bicategory K. Yes, sir.
Do you mind if I ask a small question?
No, I'll be happy to break the ice.
Maybe this is an exercise, but maybe you know the answer off the top of your head. But let's say my monoidal bicategory, let's say my bicategory was a groupoid, a two groupoid. So I guess this would correspond to a crossed module. What would the center of that look like? Sorry, does the terminology that I said familiar to you?
Yes, yeah, cross module. Well, there is, yeah, it's a braided. It'll be a braided monoidal. So there's all sorts of different terminology for these things. So what was your? Can you tell me the structure again?
Oh, sorry. Yeah, I guess I was just thinking. If you had a two groupoid with one object,
right?
Then if you're looking at endomorphisms of that single object, that gives you a two group, right?
Right.
I mean,
yeah.
So
it gets a braiding, and those things are of interest.
I was just curious if it's related, like, because you know you have two groups involved. One of them, I don't know, maybe you call it G, and the other one is H or something like that. So I was wondering if the center of that has something to do with the centers of the two groups or something.
Yeah, I don't know that offhand.
Okay, no problem. I just it's probably an exercise, I think.
Probably, yeah. Yeah. Okay. Well, thank you anyway. So the main thing we want to be talking about is the center of a monoidal category, and that is obtained in this way by taking if you've got a monoidal category, it becomes a one object bicategory, which I write as sigma V, and by just putting in one object, and then that's the hom. So I won't say explicitly what it is because probably everybody knows that, I think, but you can get that object as a descent category of a truncated pseudo cosimplicial category. So this is like a simplicial object, the beginning of a simplicial object, and I don't really want to tell you what the maps are, but that's more or less the top map there from V to VV is obtained by left multiplication. You take an object to left multiplication by that object, tensoring by that, and then tensioning on the right for the other one. And they're the main things. And so if you looked at the definition of the center of a monoidal category, that you have these half braidings, and the axiom on that involves the sort of a triangle of uses of the braiding and of the half center, half braiding, and that's like a descent condition. And so that allows you to define the center in any pseudo monoid in a braided closed monoidal bicategory as a descent construction. And this kind of limit is quite a legitimate type of limit in a bicategory. The descent object of a pseudo cosimplicial thing. and you can prove that that gives you a braided monoid R, which is, you've got to define what that is in a braided monoidal bicategory. But it's the usual process in category theory of turning equations into diagrams. Okay, so this square brackets 38 is my publication list in my publication page. It doesn't really matter. It's the paper with André Gillial on tortile Yang-Baxter operators. And the goal of that paper was to try and give an algebraic proof that the free tortile tensor category, so that's a universal property regarding the category as having structure, which is consists of the tensor product, whatever you need for being tortile, which is duals and braiding and a twist. So that's the free one of those. That's what we're defining tang to be. And we wanted to show there was also the free tensor category or monoidal category containing an object bearing a tortile Yang-Baxter operator. So I won't say what tortile means. It's some sort of compatibility with the duals and the braiding. So my student, Meitzi Schum, showed that tang was actually the monoidal category of tangles on ribbons. David Yetter defined this category of tangles on strings, and you can take a framed version of that. That was a monoidal category, and well, it's a long story, but Tureyev did various things with that, and that's where we got this idea of Yang-Baxter operators. And so we wanted to show that it had this other universal property. So we wanted to show that tang was also, what am I saying here? I've got too many things in the way here. We wanted to show that tang was also monoidally equivalent to F purely by using the universal property of F. So you've got to say as much as you can in terms of strong monoidal functors. So the property of F is that strong monoidal functors from F into any monoidal category are equivalent to just an object equipped with a tortile Yang-Baxter operator. So I want to show the sort of use of the center in doing that. So this F is we've defined it to be the free monoidal category bearing a tortile Yang-Baxter operator. So in particular, the generating object, which I'll call X, has a tortile Yang-Baxter operator on it. I haven't, where did I skip a page? Yes, oh, sorry, I skipped a page. As I say, we need to express as much as possible in terms of strong monoidal functors. So you can say what a braiding is in terms of monoidal functors. It's a strong monoidal functor from V into the center, which is a splitting for the canonical map from the center, just the forgetful functor from the center back to V. So the center of V consists of objects of V together with a half braiding. And so you just forget the half braiding and you get that. And so a strong monoidal splitting of that gives you exactly the braiding, as you might expect. You've got the half braiding and then the axiom that's strong monoidal will give you the other, what you need. We also need another construction, which is it's called the centralizer. So if you have a monoidal category, then the centralizer of an object in that category is, it's less than a half braiding. It's just an object of V together with a commuting isomorphism. And you can tensor those things in a fairly obvious way and define isomorphisms. Yeah, that's fairly easy to see how to do that. And oh dear. Doesn't want to go back. There it is. Yes, so the thing that makes that useful is that you can think of a half braiding now as a strong monoidal functor from V into this centralizer. So a half braiding on the object A turns out to be the same thing as a strong monoidal functor from V into this half center. So all you've got to understand is that the notion of braiding comes up as in terms of strong monoidal functors, and so does the you can describe the objects of the center using them as well. Okay, let's try and do this more carefully. Yeah, so the generating object bears the Yang-Baxter operator, and that actually takes the object into the centralizer of X itself, and in there the Yang-Baxter operator itself is also a tortile Yang-Baxter operator on that object of the centralizer, and you've got to see all that, but just trying to give you the idea. And so by the universal property of F, which requires you to have a tortile Yang-Baxter operator somewhere, we've got one in the centralizer, on the centralizer on that generating object. And so that gives us something from F into the center, and it turns out it does split the underlying thing there. And so that gives us an object now of the center, and it also has a Yang-Baxter operator on it, the same old Yang-Baxter operator that we've got already from F, script F. And so by the universal property again of F, you get a map from F into the center, and that gives us our braiding on F. So anyway, that's the way you get the braiding on the free monoidal category containing a tortile Yang-Baxter operator. This thing is to be checked, but I'm just trying to give you the spirit of it. Okay, have a little drink of water. So Davidoff has this notion of, I'm kind of trying to give examples now. Well, that was an example of how you use the center. I want to now move to looking at centers in other monoidal bicategories, not just cat. The center of monoidal in cat is just the center of that monoidal category. But now we want to move to other things. So there was this definition of Davidoff, which I think is quite useful. He wanted to define the center of a monoid in a monoidal category that was not braided. And so it's a fairly natural thing, I guess, to move to the center. And so his definition of the center of a monoid in a monoidal category is a map zeta from Z into A, where the Z and the U, the Z is actually in the center, and it's kind of the terminal object in the category of such diagrams. Yeah. So a terminal object in the category of diagram of pairs Z, well, the Z, U, zeta is called the full center. And he proves that ZA is a commutative monoid in the center, and he has various results. It's invariant under Morita equivalence, so that's kind of a nice thing. Anyway, my main point is that this really is an example of just a center in a different place, and it's a very simple modification of cat. You just take pointed categories. So I'm calling cat sub star, cat lower star, the two category, the pairs, a category together with an object of that category, and the morphisms are the obvious things, and well, they're kind of pseudo triangles. And as it turns out, a pseudo-monoid in there is just a category, a monoidal category together with a monoid in it. That's the standard sort of localization process. When you have a notion like monoidal or pseudo-monoid, you can sort of localize like that. And a braided pseudo-monoid is a braided monoidal monoidal category Z with a commutative monoid Z selected. And so the little proposition is that if this full center of Davidoff does exist, then it is actually the center in cat sub star. The two things together, the center of the object of cat sub star is made up of the center of the category C, the monoidal category C, and the ZA that we can derive using the terminal property of the definition of Davidoff. So that's an example. I was happy to see that Juan, in his New York talk last week, talked about mod. This is not quite the same mod, and I'm doing what he thought was a very more complicated than what he was doing, which is to think of it as a symmetric monoidal bicategory rather than as a framed bicategory. But well, what Juan looked at was rings together with bimodules. So I'm just looking at categories instead of rings, and the bimodules are very similar. So the objects of this bicategory mod are categories. You probably have met it before. The hom categories are defined as presheaves on B op cross A, which is like having a left action by A and a right action by B on a functor, and or on a family of objects of set, I suppose. And we call those modules. And the composition is by taking a coend, which is very much like just taking the tensor product of over the category in common, which is A. Oh, no, sorry, tensoring over B. So you've got a coend like that. And the tensor product of mod, to make it into a monoidal bicategory, is just the Cartesian product of categories, and that's not actually the product in mod. It's a real tensor product, and it is Cartesian in some sense, but it's done by Walters and Carboni and so on. But it's not the ordinary Cartesian product. In fact, the Cartesian product in mod is co-product of categories. And so it's actually a kind of additive thing. So it's quite a nice bicategory, I think, anyway. And it behaves a lot like the category of vector spaces because of that additivity. And it's got nice duals. The opposite of a category is a dual in the monoidal sense, or the bimonoidal sense. And ordinary functors sit in there in mod by that rule. So if you've got a functor f from A to B, then you get a bimodule by taking f lower, calling it f lower star of B comma A is just putting f in the covariant position. And if you put it in the contravariant position, you actually get an adjoint in the technical sense of a bicategory. So these particular functors arising this way do have right adjoints in mod. But I don't need that, I don't think, here. Okay. So as I said before, I'm going to regard monoids and groups as one object categories, and the object of the group is going to be denoted by O sub G, little o sub G now. So the morphisms of the category are the elements of G, but I'll still write A lies in G to mean that A is an element of the group G. And we'll use conjugation notation. Probably only need one of these, but if you put the C up on the top, it's on the left, it's C to the minus 1, and A on the right. So they have nice exponential rules and so on. So like every category, G is actually a promonoidal category because, well, we're in cat, and cat is Cartesian. So in every category in a Cartesian, well, yeah, every object of a Cartesian closed category or Cartesian category is a comonoid, and that allows you to get a promonoidal structure. I'll say it explicitly here. Or did I say that promonoidal categories are the monoidals in mod op? Yeah, so maybe mod op is, I think Bob Perret likes using what I'd call mod op rather than mod, but this is a good reason for it, I guess. It's just that Brian Day wrote his thesis putting convolution structures on the pre-sheaf, not on the pre-sheaf category, but on the covariant functors from the category into V or into the sets, rather than taking the pre-sheaf category where you take contravariant functors. So anyway, the promonoidal structure is really a module from G to G cross G, and it's given in this way, in an obvious sort of way. And if you have a group morphism, then that's an example of a functor. And any functor, well, you're probably more familiar with the case where it's a fibration, when you end up getting a pseudo functor by taking the fibers. But Benabou pointed out you can do this for any functor. If you have a functor from H to G, then you can get a pseudo functor. Well, you can get a normal lax functor. Normal just means it preserves the identities, and lax functor means that it only preserves the composition up to a map. But of course, we're dealing with groups here. So anyway, we get a normal lax functor, and if that group homomorphism is surjective, then that's the same thing as saying that it's a fibration as a functor. It's a fibration if and only if it's an op fibration, if and only if it's a Giraud Condorcet, has the property of being a Giraud Condorcet, and that's the same thing as just being a surjective group morphism. So in this case, it's actually a pseudo functor going from G into mod op. So I'd like you to think of this mod op as being quite a nice thing like vector spaces almost, because you've got the direct sums and a lot of other things, duals. So I've just described what this thing does. The fiber of the functor pi over the object is actually just the kernel of the group morphism. We're just interpreting all this fancy category theory in terms of ordinary group concepts. That K is a one object category, and you can define it the way it's defined as a module, HA, because I'm trying to define a pseudo functor from G into mod. So if you take a morphism of G, that's an element of G, you've got to get a bimodule, and it's just the elements of H that map onto that A. In particular, it is strict. It is normal. Yeah, anyway, it's getting a bit technical, I guess, but you can also prove that it's strong monoidal. No, strong. Yeah, that's pseudo, not lax. Yeah. Okay. So I'm getting a bit technical, I guess, but this thing is actually a bijection. It preserves composition up to isomorphism. So now what I'm really trying to get to is the fact that this H is actually a monoidal. So coming from this group homomorphism, we're actually getting a monoidal in the pseudo functors from G into mod op. And the formula for it, so remember monoidals in here, that point-wise, they're going to be monoidals in mod op, which are promonoidal categories. And so you've got this square brackets operation, and you've only got this one object, so its value at that one object is given by pairs coming out of the kernel, and that's how it's defined on morphism, so I won't prolong that too much. Did I do that? Okay, yeah. Sure. Oh, sorry, I'll just. Okay. So I want to get back to centers. So if you take a group regarding it as one object category and then take the category of automorphisms in that, that gives you a nice groupoid. The objects are actually the elements of the group. Morphisms are elements of the group again. A morphism from A to B is well, it's basically something that takes, it's an element which takes A to B by conjugation. So, but naturality, or the square that tells you it's a morphism of the automorphism, is that FA is equal to BF. So also given the group, we can define a G set, namely taking conjugation. So it's G as a set acted on by conjugation, and I'm writing that as G conj, and it has the property that the slice category of that, well, it's actually a monoid in G set by just the multiplication of the group. So G conj is a monoid in G sets, and it's equivalent to, this slice category is equivalent to this is the process of taking the category of elements, right? So you can think of G conj as being as a functor from G to sets, and then take the category of elements, and that gives you G aut. Okay, but G conj is a monoid, and therefore you get a monoidal structure on G aut set, and that means that G aut is also a promonoidal category. So yeah, this is called 2, I guess. Yeah, 2. So the left-hand side is a monoidal category. So you've got this promonoidal structure on G aut, which is defined that way using conjugation. It's actually braided. So you can talk about braided promonoidal categories. Well, it's because they're just monoidals in mod op, so it makes sense. And it's also actually, we've got a twist. That's to do with the fact that well, the inverses in G give you joules and so on. So you expect to have a twist. So anyway, it's a fairly nice promonoidal category, this G ort. It's star autonomous and promonoidal. So the main result I wanted to get to is that this braided monoidal G ort is actually the center, the monoidal center of the monoidal G in mod op, and this convolution braided monoidal category is braided monoidal equivalent to the monoidal center of G sets. I guess this might be well known. I guess it's discovered by a lot of different people, I think. So the center of just G sets, that's a very simple example of a center, is actually a pre-sheaf category again. And Brian Day and I have a few papers on when the center of a pre-sheaf category can be a pre-sheaf category again. So it's actually braided, that becomes balanced when you transport the twist. So you can take that group homomorphism, surjective group homomorphism we had before, and we can also make the thing, this H into an H ort, which is another pseudomonoid. So this ort process is just really homing in from a particular small category, the free living automorphism category. Doing that takes the fibration pi from H to G into a fibration from H ort to G ort, and we can do the process of taking it's like that's the Benabou generalization of the Grothendieck construction to get a lax functor or pseudo functor. So we get a pseudo functor from G ort to mod op. And I mean, there are too many details, obviously, to read it all in detail here, but it becomes a pseudo functor in the way I've described. It's just it's the same on the Benabou construction is still taking the fibers and making it just into going into mod instead of going into cat, just like the Grothendieck construction. Generalizing the Grothendieck construction. So it turns out this H ort is a balanced monoidal in the pseudo functions from G ort into mod op. And I've laid out the structure there. Probably a bit difficult to take in at the moment, but there it is. And it's braided. So I'll leave that for a second. It's got a twist. Oh, where's the theorem? Oh, there it is. So what I'm claiming is that and this is joint work with Branko, as I acknowledged at the beginning of the talk. So that's really an example of a high full center. So I'm showing that the Davidoff center idea, full center idea, maybe is worth considering at a higher level as well. There's an obvious lifting of the way Davidoff did it, but you can also define it as a kind of higher descent category. And so the full center of a monoidal in a monoidal bicategory is going to give you a braided monoidal in the monoidal center of the bicategory. And what I'm claiming is that the braided monoidal bicategory of pseudo-functors from G aught into mod op is the monoidal center of the monoidal bicategory G mod op, pseudo-functors from G into mod op. Just the same as it was when mod op was just sets and we're taking just ordinary functors. Yeah, so what I'm claiming now is that this H becomes the full center in here in pseudo G mod op. Sorry, if you take the monoidal H in the pseudo functors from G to mod op, then you get this thing H aught, which is a braided monoidal in pseudo functors from G aught to mod op. And remember, that's the center. So pseudo G aught mod op is the center of pseudo G mod op, and this H aught is the center of H in the sort of full center sense. Okay. To actually get back to the sort of thing that Turev and Virolisi were talking about, you need to use the pseudo functor that I mentioned back there that you can get from mod op back into VCAT. So for them, VCAT would be, V would be vector spaces, so you'd be dealing with V linear, with K linear categories, probably K is of complex numbers, say. And then they get their result, which is Muger's result. But you need this pseudo functor to turn all the stuff I was talking about into actually K linear categories. Yeah. So I think that's about it. It seems to be a bit technical. I hope it wasn't too bad. Thank you, Juan and everybody. Hope I didn't lose too many people.
Thank you very much, Ross. It was a lovely talk. Thank you.
Okay.
Well, do you mind if maybe there are some questions or comments? Well, for everyone, I'm just letting you know that Ross has to leave a little bit early. He has a commitment.
20 or something. Yeah.
Yeah, well, let's, if anyone has any questions or comments, please unmute yourself and ask them, please. Well, there doesn't seem to be any questions. Yes, please.
Just like this reminds me of something that I was studying last year about Morita equivalence, and one of the results, if you have a Morita equivalence between if you have the Morita equivalence between R mod and S mod, the centers are equivalent. And I was wondering if like there could be something like constructed over monoidals, like to try to something like a Morita equivalence over monoidals, and to see if the center behaves similarly.
What was the last thing? No.
Just because, like,
Morita equivalence of,
like if there's could be a way to construct the Morita kind of Morita equivalence over these structures in order to and to see if
what
like,
structures
if
are you
that,
saying? What
like these braided monomials, the category, like, I would like to, if that, sorry, just trying to organize my thoughts.
That's fine. Yeah, I'm just trying to, yeah.
One professor told me that Morita equivalence seems to be an structure that it could be like more abstracted in different terms, and a Morita equivalence is a relationship between rings. So
Yes.
I was wondering if you could try to go to a similar construction for monoidal, and maybe after you have this Morita in over monoidals, these equivalence Morita equivalence over monoidals, can you ask the question then what happens to the center of those monomials?
Yeah, well, so Morita equivalence is actually just ordinary equivalence in the bicategory of modules. Yeah, so that's the first thing, I guess. And considering the Morita equivalence of monoidal categories, I guess is what one of the
Yes.
types you're thinking about. Yeah. I actually had a student who did that. Scott Johnson wrote a paper way back in the late 80s, I think.
Oh.
Yeah, but it's not that, it turns out. So if you look at, what is it? Something very trivial, if you think of rings, monoidal, Morita equivalents just for rings themselves. If you actually look at the monoidal structure in the bicategory, on the modules category. So you take a ring and look at the module category, and then look at that as a monoidal category. Then they're equivalent, if and only if the rings are isomorphic, I think. Or is that just for commutative rings? No, I think that's true. If you take the monoidal structure, you put a count on the bicategory, on the category of modules over the ring. Yeah. That's all. I think that's about all I can say. Yeah.
Okay.
But I mean, there must be some higher mod op as well. That's what this is leading to. But it's all a bit scary, and yeah.
Yeah. And
I'd like to see a reason for doing it first before going ahead and doing that kind of thing. Yeah. Thank you.
Thanks.
Thank you very much, Luis. Are there any other questions or comments? Well, there doesn't seem to be any more comments. Well, yeah, I think. Well, thank you very much, Ross. It was a great talk. Thank you for mentioning my talk.
No, I enjoyed your talk. I think it was very good.
Yeah, I didn't mention mod op. I don't know why. I think a mod is a bit easier. And yeah, well, anyway, thank you very much. Thank you very much for coming. It was great having you here. Hopefully, oh, well, there's another question. I'm sorry.
Okay.
Well, there's a thank you from Arthur. Yeah, I think we can close the session. Thank you so much, Ross, and hopefully we'll see you at some point. Well, meet in person, and hopefully see you in Mexico in person sometime.
Yeah, okay, that'd be great.
Yeah.
Thank you for all, organizing and for meeting these people.
Yeah. Yeah, I think, well, I don't know, maybe this is a bit off the record, but could you say a bit more about the history of how you got involved in centers?
In centers?
Yeah.
Well, getting involved in braided and ordered categories was the first thing.
Yeah.
Yeah. So that was, well, as I said, it was this conversation that was reported to me by Lavia and Bob Walters.
Yeah.
And so we knew that if you want VCAT to be monoidal, you need V to be, well, what Arlenberg Kelly had was that it had to be a symmetric monoidal category, and they treated that case.
Yeah.
So to get a tensor product of enriched categories, you need the V to be. So anyway, Bob Walters and I developed this stuff about enriching in bicategories.
Yeah.
And so in order to get the monoidal structure on enriched categories over bicategories, what do you do instead of symmetry? And so then we realized that or W mod, if W is a bicategory, W mod, W itself had to have a tensor product on it as well. Yeah. So then in the one object case, when I checked what really happens there, it turns out to be a braiding. And so then there are all sorts of things from getting from this point of view that leads you to the center, as I was trying to explain. But of course, Andre's motivation, maybe he knew all this anyway, but he also was inspired by homotopy theory and was had worked with Tierney on homotopy types.
Yeah.
And they have this model of homotopy 3 types with groupoids, braided groupoids.
Okay.
So he was coming from that angle. Yeah. So I was actually giving a talk in McGill on well, the nerve, the higher nerve of an N category.
Yeah.
And Andre was in the audience, and Andre said, oh, the associativities don't really matter. It's more important as the commutativities. And I said, well, you get the commutativities thinking about this conversation with Bob Walters,
Yeah.
that you get the commutativities, those middle 4 interchanges and things like that. So it's all part of the higher structure anyway. And so then I went back and checked what happens, and the rating came out, and then Andre said, oh yes, he knew. And so we started talking about that and thinking about so I gave a talk that year at the Isle of Thorns in England.
Yeah.
And I called it slightly incoherent symmetries because I hadn't come up with the name braided. We knew the braided groups was good. My main thing for that talk was the coherence theorem for braided and monoidal categories, and yeah, I didn't know that Andre was actually had all thought about that too. But yeah, it's kind of an obvious thing that where McLean had the symmetric groups for his coherence theorem. The braid groups, you expect more one for that. So by the time I actually gave the talk, I thought of that braiding, like we have a symmetry on a monoidal category, we should have a braiding on a similar word.
Yeah. Yeah, braiding was a lot.
Of course, then there's the Russians knew a whole lot of this stuff anyway. That was kind of independent at that stage. But then we saw Grinfeld's talk at we found out about Grinfeld's talk at the International Congress on quantum groups. He had the Grinfeld double in that, but that was about a year later. Of course, he knew it by then anyway. I don't know exactly. I don't think he ever really published the center in a paper, but various people have reported that he knew well all about it, and that was the connection between the double of the Grinfeld double of a Hopf algebra and the center. It's probably known well to him.
Well,
yeah, so I guess that's where it all came from.
Yeah. Oh, that's
also Menon. Yuri Menon going to Montreal. In those days, it was a bit difficult to get out of Russia too.
Russia.
Delayed, but he did come and gave some talks, and that was where we started taking the Yang-Baxter operators seriously. Yeah, because Andre and I were there in those talks.
So this was late 80s or
late 80s? Yeah.
Okay.
Yeah.
Well, yeah. Well, yeah. No, it's a great story. Thank you very much.
Oh.
Yeah.
Thanks.
Well, we had a talk by. Well, I'm not sure if you've heard of him. This Colombian mathematician, Bernardo Uribe. Well, the talk before you. And he was talking about this. Well, he just he talked about a lot of things, but essentially, I think what Luis was asking. So he was thinking about Chern-Simons and how let's say graded vector spaces are Morita equivalent if and only if the centers of the categories of representations of the doubles of the Hopf algebras of the group grading with the twisting cocycle are isomorphic, and then Chern-Simons are the Chern-Simons theories are isomorphic, and then that was interesting, and next week we'll have Ingo Runkel, as you mentioned, talk about hopefully about centers as well. So
unfortunately, it's at 4 a.m. for me in the morning.
Well, we'll have it online. I think Arthur, what time is it in France?
I'm actually not in France right now.
You're not in France. Okay, yeah, that was. I thought you were.
That's why.
Yeah. Well, yeah, we'll have it on YouTube if you want to watch it at some point.
Yeah, that's very handy. Yeah.
Yeah, I mentioned your talk to him, so hopefully there will be some continuation or something. Yeah.
Things come from that. Yeah.
Yeah. Well, thank you so much, Ross. I think maybe we all have to leave.
Yeah. Okay. I probably should.
Okay. Well, yeah. Thank you so much, Ross.
Thank you.
Yeah, it all worked out pretty. The slides worked out great.
Feeling a bit better about the slides now.
I think it might have been the clicking. I think you went at the New York New York City seminar. I think you were clicking with a keyboard. I think
that's right. And I wasn't using this one. I was using the PowerPoint or whatever it's called instead.
Right.
Yeah, instead of.
Yeah, that might have been it. Yeah. Well, it worked out great.
It wasn't real PowerPoint. It was a preview version of that.
Yeah. Well, okay. Well, thank you, Ross.